talk. So Matt Wheeler is a postgrad student at University of East Anglia, working with Hader Solomon and Magnus Bohr. You can see his title there. So Matt, when you're ready, please just go for it.
Right, thanks very much, Andrew. Thank you to 2K for an interesting talk as well. I'd just like to thank the organisers for giving me the opportunity to talk about my work here. So as Andrew was saying, I'm a PhD student at UEA. My work looks at sort of dynamics of vortices in multi-component systems, so two components, and we also look at spinors as well. And today I'll sort of be talking about a bit of recent work that we've done, which is on the relaxation dynamics of half-quantum vortices, or HQVs, in a 2D, two-component BEC. So as sort of a very shameless self-plug, if you're interested in any of the work, we sort of wrote about it for EPL recently for one of their focus issues, and that is the reference there if you'd like. You don't have to. I'll just give a very brief outline of the talk. So we'll start with some very simple background and motivation of why we want to study this sort of dynamics. Then we'll go into the model, so looking at how we actually model the dynamics and what a half-quantum vortex is, and then sort of talk about the initial state and the setup that we use. And then thirdly, we'll get into our results. So we start initially with some sort of spatial aspects of the dynamics. So we'll look at the kinetic energy spectrum, and then we'll move on to the more interesting temporal aspects by looking at sort of correlation lengths and the vortex number. And then I'll just briefly conclude with some conclusions. So just to start with some simple background, as I'm sure you're all very aware, I'll just briefly go over what a BEC actually is. So if you consider sort of a box of bosons, each boson has its own wavelength. As you cool this box, the wavelengths sort of get larger and larger until eventually you'll sort of get to this critical temperature where all these wavelengths they're overlapping, and it's described by this giant coherent matter wave, which is your Bose-Einstein condensate. And these are obviously very, very interesting systems to study. They exhibit novel properties such as superfluidity, and they also give rise to topological defects such as quantum vortices. And you can also have sort of quantum turbulence in the system as well, which is sort of the presence of many of these topological vortices, these quantum vortices. So here on the left, you sort of have your classical system, classical turbulence. This is the atmosphere of Jupiter. You have many vortices, and you have this sort of chaotic turbulent system. And then sort of the other end of the spectrum, you have this sort of like quantum vortex tangles. And so my work is focused more on these sort of quantum vortex turbulence systems. So I'll just go into our model and what we actually are looking at. So we're considering the relaxation dynamics. So essentially we're starting with some very initial turbulent system full of many of these half-quantum vortices, and then we're sort of evolving the system in time. And what happens is sort of vortices will annihilate with one another and the system sort of relaxes. And the way that we model these relaxation dynamics is through the two-component Grosby-Teskey equations, which is given by this here. So this is a pair of coupled GPEs. And so you sort of have, again, your kinetic energy operator, and then this term here sort of accounts for interactions of atoms in the components. Then you sort of have this sort of new term that arises, which accounts for interactions that are in the opposite components. And we're considering the special case of equal intra-component interactions. So G1 is equal to G2 is equal to G, and also the special case of equal densities of both components as well. So what we are doing in our simulations, we are essentially varying this parameter that we call gamma, which is the ratio of the inter to intra-species interactions. So we are keeping G fixed, and we are varying G12 within our simulations. And in the system, there's two relevant healing lengths. You have your typical density healing length, which is sort of the length scale over which the density heals as it's perturbed. And you also have what's called the spin healing length. And the spin healing length is what sets the core sizes of the vortices in our system. And you can see this is actually dependent on gamma. So as we are varying gamma, we are actually increasing the core size, as you will see later on. So I'll just briefly go over what a half-quantum vortex actually is. So if you consider a two-component wave function, which very generally is given by something like this, so you have mod psi 1, mod psi 2, these are just sort of square roots of densities. And then to this, you can sort of couple some complex phases, theta 1, theta 2. And you can kind of recast this into the form that's on the right here. So you end up with these angles, capital theta and capital phi, and these are used to sort of highlight what a half quantum vortex actually is. So in order to actually construct a half quantum vortex, say you have a phase singularity in the psi1 component that sort of winds by 2 pi around a point. You can sort of write the wave function as something like this. So again, you've got your densities, and in this component we have e to the I phi. Phi is essentially just the azimuthal angle around this defect, around the vortex. And again, you can sort of do some recasting magic and you get it into the form that's very similar to what's above. And what actually happens is, if you traverse a point around this vortex, these angles here, theta and phi, they will actually wind by pi. So this is sort of where the name half quantum vortex comes from, because it's carrying this half quantum of circulation as compared to a scalar vortex in a scalar condensate. So you can see here on the right, this is just sort of a phase diagram of this angle theta around some vortex that's in the center, and you can see it does actually wind by pi around this. So this is where the name comes from, and this is what we're studying in our system. So I'll actually just talk about our initial state briefly. So essentially, like I said, we want to start from this sort of initial turbulent, chaotic regime that's full of many, many vortices, and then relax the system in time. And the way that we sort of do that is we'll start with this sort of like uniform grid of vortices. So we use 48 squared vortices in each of the components. And so this is also a periodic domain as well. There's no trap or anything in this. And this is sort of arranged like a checkerboard pattern. So you'd have something like a positive vortex, positive, negative, and so on and so on. And then what we sort of do is we will take each position that's in this uniform grid and kind of just nudge it by some small amount, by some random amount. And it sort of creates this like pseudo-random initial distribution of vortices. Then we'll do a very, very brief imprint the cause in imaginary time. So as you imprint imaginary time, essentially the cause fill. And this is essentially just a brief snapshot of what it looks like in our system. So this is the density of the psi1 component. And you can see the vortices in this component are given by these density depletions. And you also see these very bright red sort of density peaks. So what happens is when the cores form, atoms in the other component fill the cores. And so you can see these bright red peaks actually correspond to vortices that are in the other component as well. So we'll start from an initial state that's like this, and then we'll evolve the system in time and look at the relaxation dynamics. So I'll get onto some results and show you what we've essentially looked at. But first, we'll just have a brief look at what actually what the dynamics actually look like. So this is just a snapshot of a simulation for 3 different gamma. So here on the top, you just have density plots, and here on the bottom, we have what's called the pseudo-vorticity. So this is essentially just it's the curl of the mass current, and it just allows you to find where the cores are in the system. So the color essentially corresponds to the circulation. So here you've got blue, which is positive circulation, and red, which is negative circulation. And you can see if you look at the sort of density plots, you see this sort of a lot of background noise that's generated from the annihilations, and as you increase gamma, you notice there's fewer and fewer vortices. So these are all at the same point in time, but we'll talk about why that is the case later on. And again, you can sort of see these very bright red density peaks, which are corresponding to vortices in the other component. So the first thing that we actually looked at was sort of the spatial aspects of these dynamics, and we considered the kinetic energy spectra. So I'll give a brief overview of how you actually construct this. So if you think about the kinetic energy, you can sort of split it into a sort of a classical velocity part and a quantum pressure part. And this classical velocity, you can also further decompose into an incompressible contribution and a compressible contribution. And so these are the generalized velocities for these. So you have, again, incompressible, compressible, and you also have quantum pressure as well. And then to actually extract the spectrum, you will perform Fourier transforms of these quantities and essentially integrate over an angle which returns some 1D spectrum that's based on the wave number k. And again, you do this for all 3, so you have contributions for incompressible, compressible, and quantum pressure. And then from these you can actually extract the occupation numbers as well. So here, this is the plot of the occupation number as a function of k, again for our 3 contributions. And there is also this black curve, which is essentially just the total occupation number of the system. So you can see the sort of like there's two different things happening here. There's this sort of like shoulder that's forming. Oops. So at these high wave numbers, you have a scaling the total occupation that is roughly around k to the minus 2. And you'll see that this is due to essentially the quantum pressure and the compressible components dominating these high wave numbers. And again, if you sort of look at the other end of the spectrum, you'll see there's this k to the minus 4 scaling of the total occupation, and this is due to the incompressible. And so this is for a very late time within our system, sort of like the very, very end point that we looked at. And this is sort of very similar to results that have been seen in scalar BECs before for containing scalar vortices. So the main takeaway is that even though we have this system of different types of vortices at sufficiently late times, we are actually recovering results that are similar to scalar BECs. And should also point out as well that the scaling of this energy, so this k to the minus 2, k to the minus 4, is actually insensitive to gamma. So we could go as low as gamma as 0.1, we can go as high as gamma as 0.9. You would essentially just recover a very, very similar picture. So it's essentially saying that the spatial aspects of this dynamics, at least at late times, aren't particularly interesting. So we decided to focus more on the sort of temporal aspects and see if they reveal anything, which they do. So the first thing we did was sort of look at these things with correlation functions. And these are essentially just ways to tell how well correlated a system is. So in our system, we have one that's for the spin, which is this top part, and one that's for the mass. And you can see that they're very, very similar to each other. What sort of happens is, so each line in this represents a different point in the, different point in time, and you can see as you go along and increase in time, the correlation functions are sort of decaying over larger and larger distances. And essentially, that is just saying that there is sort of long range order that is appearing in the system, and you have these sort of domains. So as the vortices are annihilating with one another, you have these domains that are growing in the system. And essentially, you can show that these correlation functions sort of collapse to this universal time-independent function when you scale it by an appropriate correlation length. And this is showing sort of what's called self-similarity. So the system is self-similar at different points. So this is what this inset is showing here. You basically take these correlation functions, you sort of scale it by some correlation length that's a function of time, and this collapses. So from these correlation functions, we actually do extract this correlation length. And the way that we do this is essentially it's the length scale over which the correlation function decays to a quarter of its value, or equals 0. And what I essentially mean by that is if you consider these correlation functions, if you just take the point as, the correlation length is essentially the point at which this correlation function decays to around 0.25. And if you go from left to right, you'll see that the correlation lengths are actually growing larger and larger with time. So this allows you to sort of plot these quantities as a function of time. And this is sort of where we first saw some quite new interesting behavior happening. So here we have the correlation lengths for the spin and mass part for 3 different gamma. If you consider this bottom line here, so this is for relatively low gamma, so 0.3. And you can see it's sort of just an almost constant growth of the correlation functions. So nothing too interesting is happening there. However, what you might notice is if you start increasing gamma, so gamma is 0.6, gamma is 0.8, you can actually see at these sort of early intermediate times, there is a rapid growth of the correlation lengths. And then eventually at sort of later times, it sort of again peters off to this, what's roughly around a t to the 5th kind of scaling. So this is very indicative that something is happening differently in the dynamics. So gamma is somehow affecting these early time dynamics. So we sort of wanted to set out and try and investigate what this actually was. And the way that we sort of did it was by looking at the vortex number as a function of time. So you essentially just count the number of vortices that are in the system, and you can plot this as a function of time. And that's what these plots are here on the right. So these are again for 3 different gamma. You have a very low case, gamma is 0.3 here. Again, it's just sort of almost constant decay of the vortex number. And there's nothing sort of different happening at these early times. What we do notice is once you start increasing gamma, especially in the 0.9 case, you can see there is sort of a very different early time scaling happening. So there's a rapid annihilation of these vortices at these sort of early intermediate times. So it's sort of alluding to that there is a gamma dependent scaling on the vortex number at these early times. And this black line here is essentially from a scalar BEC simulation that we did. So same kind of setup with sort of like perturbed grid, evolved this in time. And essentially we just included this to sort of show that at these later times in our simulations, we are recovering scalings that are very similar to scalar BECs at some similar point in evolution. But it's these sort of early intermediate times that are very, very interesting. So obviously there's something happening here at these early times. So we kind of wanted to understand what it was and what was going on. And in order to do that, we sort of had to understand some work that was done by Kenichi Kasamatsu back in, I think it was 2016. And essentially there's this paper here that's cited at the bottom that was essentially looking at the interactions of half-quantum vortices in two-component BECs. And this plot is from their paper there. And essentially it's just showing a half-quantum vortex dipole, so positive circulation, negative circulation, and it's showing the trajectory for different gamma. So if you consider the case of gamma is 0, so this red line, you get your stereotypical sort of vortex dipole motion that move parallel to one another. But actually what they found is very, very interestingly, if you increase gamma, and you go above some certain thresholds of 0.7, 0.8, what actually happens is it sort of deviates from this parallel motion and they sort of move together and they eventually annihilate. So what it's showing is there's some kind of attractive mechanism between these half-quantum vortices of opposite circulations in the same component that causes them to sort of move together and eventually annihilate. So what we think is happening sort of at these early times in our system, sort of when all the vortices are very, very close together, the intervortex distance is small, we sort of think that there's this attractive mechanism that is taking precedent and it's sort of causing this rapid annihilation effect to happen. And the reason why we don't think it's happening in sort of these later times is because as the vortices rapidly annihilate with one another, the intervortex distance, so the separation essentially of the vortices gets larger and larger and larger. So this sort of attractive mechanism is not happening over these sort of longer distances. But not much is actually well understood about this attractive mechanism, at least not to my knowledge yet. So this work was done in 2016. I'm not sure if any more work has been done on it since. They essentially tried to derive a point vortex model, but found it sort of broke down for these very, very high gamma, and it doesn't explain this sort of attractive mechanism. So there's a lot of open work there to be done. And I think it's a very, very interesting problem. And just very finally, we just sort of wanted to hammer home this point of how much of an effect gamma does have on the decay rate of these vortices. You can essentially take a very simple kinetic-like equation of the vortex number, so something like this here. You can solve it and you get something like this. So the vortex number scales like t to the minus 2 over z, where z is some exponent. So what we decided to do was sort of take this region in time where you were seeing this rapid decrease of the vortex number and calculate the exponent. And what it allows us to do is sort of plot this exponent as a function of gamma, excuse me, which is this plot on the right here. So you can see for sufficiently low gamma, like 0.6 and below, you sort of just get a very minor decrease of this exponent. But there's almost like this cutoff here where after this point, there is a rapid decrease of this exponent, where the sort of new annihilation effect is prevalent and it's causing this rapid decay. So I think it's very interesting behavior. I'll just very briefly conclude. So we had a look at the relaxation dynamics of half-quantum vortices in this 2D two-component system. And just by looking at the spatial aspects, so this was very late times, we were sort of obtaining results that have been seen in like scalar BECs. And by actually investigating the correlation lengths, we showed that increasing gamma sort of leads to a faster growth of the correlation lengths above some threshold. And again, this is sort of confirmed by looking at the vortex number, where we see this sort of very steep decay of the vortices at this sort of intermediate and early times. And what we think is happening is this sort of this attractive mechanism that's not really well understood that happens between these vortices in the same component, and they have opposite circulation. And we think this is causing the sort of rapid annihilation of the vortices at these early times. Because of, so when the vortices are all annihilate and the intervortex distance gets larger and larger, we think this force is not having an effect because it's not extending over these much larger distances. So like I said, it's a lot of open work to be done to understand this sort of attractive mechanism. It's not really well understood at the moment, but it's clear that it does have an effect on the dynamics of the system. So yeah, that concludes my talk. Thank you very much for listening. I'll happily answer questions if there are any.
Thanks very much, Matt. Yeah, there are a couple in the chat. I don't know if you can see it easily or if you want me to read them out. I'm happy to do.
Can I see them? Yeah, I think I can.
Maybe for the sake of the recording, I don't know if they come up, so I can read them out. So
yeah, if you read them.
The first one's from Marek. It's how is the initial state generated? Is the square lattice somehow a stationary state of the system?
Let me just go back to here. So yeah, so this is initial state. So essentially, we are just picking positions, and then we are sort of generating a phase profile using these positions. So the formula for generating a phase profile is quite complicated. It comes from this paper. I think it was done by Tom Billum a while back. So we essentially just pick all these positions, generate this phase profile, and we will essentially construct a wave function like this and relax it in imaginary time very briefly, just sort of to form the cause. But it's just a very brief imaginary time evolution.
But your boundaries are periodic. Does your initial condition,
yes,
is the imaginary time relaxing it to a state where it then satisfies? Because I guess the lattice originally is not satisfying periodic boundary conditions, but your imaginary time.
So,
yeah. Sorry, go on.
No, please answer the question, then I will follow up on my own question, but please answer the...
Yeah. So, I mean, it's just a very, very short imaginary time. So I think the lattice, yeah, so maybe it doesn't account for periodic boundaries, but I think the imaginary time evolution sort of fixes that, so to speak. But it's just a very short imaginary time evolution that we do.
So my understand. So am I correct when I say that the initial state that you generate, it's not a stationary, it's not a solution of the time independent BEC equation. It's just some non-equilibrium state that you just impose, right?
Yes, exactly.
It's not a solution to the equations.
No.
So Callie has a question. So can you remind me why the spin healing length sets the length scale for the vortex cores?
Yes. So I think it's the larger healing length that sets this. I don't know if this is an energetic argument. I forget the details, but essentially because the intercomponent interactions are typically smaller than the intracomponent interactions, essentially means that the spin healing length is larger than the density healing length, and I think it's to do with sort of this repulsive interaction that sort of expands these cores and fills them with atoms, and it's set by their spin healing length. So I can't remember the exact details of why that is the case. But I think it's because it is the larger of the two, and that's why it's set.
Okay, thanks very much, Matt. Just about on time, but I'm happy to take another quick question if anyone.
Hi, excuse me. Hi, Matt. Thanks for the talk. I just wondered, is there kind of an analytic or a physical argument for why at later times the vortex number goes like t to the -2/5?
So do you sort of mean as opposed to a t to the -1 that you would typically see?
Yeah, absolutely.
Yeah. So this is essentially a timescale argument. So this black line here is essentially, so what we did actually, and the referees sort of asked us to do this for this paper, is we sort of took this scalar simulation and just ran it for very, very long times. And what we actually do recover is a t to the -1 scaling of the vortex number. But essentially for this system, we are just focusing on these sort of early and intermediate times. So this is sort of like before the transition into a t to the -1 that you would typically see for those kind of simulations. But you do eventually see them. And I think eventually we would sort of see them in these two component systems as well. The problem is for very, very high gamma, you have very few vortices left in the system because of the annihilation. So we don't know if there is enough vortices to sort of facilitate the transition to T⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻
Thank you.
You're welcome.
Okay, I think that's where we'll end it today. So thanks very much to Sasuke and to Matt for two great talks.